Okay, the seminar today is going to cover the measurement of the Seebeck coefficient and electrical conductivity, introducing the measurement method. My name is Robert Campbell. I work in the Netsch Instruments North America location. I'm the Applications Laboratory Manager. My background, I've been a scientist and lab manager for Netsch in the Boston, Massachusetts area since 2001, so about 14 years with Netsch. And I perform thermal analysis and thermophysical properties measurements of a wide range of materials through our activities here in the Applications Lab in Burlington, Massachusetts. So this is a outline of the presentation today. We're going to introduce the Netsch model SBA 458 Nemesis. We're going to look at the measurement method in detail, discuss the both measurement electrical conductivity and Seebeck coefficient, how those are implemented. We're going to look at the mechanical setup, how the samples are mounted and the measurement is set up. We're going to look at the features of the software. And we will discuss the key features and advantages of the SBA, look at some specifications, and then finally look at applications. So to introduce the SBA 458 Nemesis, a little bit on the name here. This is a tradition of Netsch to use names from Greek mythology. And for this product, Nemesis was chosen. So I hope that if you do encounter this instrument, it doesn't become your nemesis, but it is a name from Greek mythology. Okay, so the measurement that we can perform with the SBA 458, of course, is the Seebeck coefficient, S, and the units for Seebeck coefficient are microvolts over K. We can measure also electrical conductivity, sigma, in Siemens over centimeter. Looking at the instrument itself, if any of you are familiar with the LFA 457, this picture probably reminds you of the 457, of course, because it's essentially the same platform. And the furnace is the same that's utilized in the LFA 457. So this is the furnace here, and we have electronics and control below. There are also some other components, power supplies and meters that are part of the system. Okay, so the main application, of course, for the SBA 458 is in the field of thermoelectricity and the determination of the figure of merit. So this tells us about the efficiency of thermoelectric materials, and we normally use the figure of merit zeta times the absolute temperature expressed here. And this includes the Seebeck coefficient, S, squared times the electrical thermal conductivity divided by the total thermal conductivity times the absolute temperature. And as you may be aware, of course, there are a lot of trade-offs in trying to increase the figure of merit. And so these properties, measurements of these properties is quite important. Of course, Netsch, as you probably know, has capabilities to measure thermal conductivity. And primarily with the flash diffusivity method, or LFA, we are determining thermal conductivity through the equation presented. Lambda is equal to the density times specific heat times thermal diffusivity. So in combination with the LFA, to measure thermal conductivity, or possibly DSC to measure specific heat as well, and the SBA 458, we have all of the tools required to determine the figure of merit. And so we will move now to discuss the measurement method for the SBA 458. So this diagram shows you the sample setup. You can see that the entire setup is located inside the furnace. The setup is heated by the furnace, temperature is controlled so that we have a uniform temperature across the measurement setup. And the setup includes our sample here is in blue. It's pressed by a weight, which we will see later, onto 4 points. And these 4 points include current pins and thermocouples here. And the sample is supported by a ceramic, that's actually an alumina plate. Within that plate on each side are microheaters. So the force that's applied by the weight on the sample presses against these current pins and thermocouples through a spring. So we have a defined force for the contact between the pins and the sample. Additionally, the presence of two heaters allows us to apply temperature gradient in both directions, which we'll see coming up when we measure the Seebeck coefficient. So we can produce a temperature gradient from right to left or from left to right in this setup. And this measurement, the measurement process that occurs is to heat the sample on the support in the furnace until we reach a stable temperature. So we have to wait for temperature stabilization, and then we start our measurement process. So we measure first the electrical conductivity, then we measure the Seebeck coefficient, and then we heat up to the next step for an arbitrary number of temperature steps, which we can program. So first, to describe the measurement of electrical conductivity, we're using the 4-point measurement, and we're able to supply different current values in different directions. So we measure the voltage at these 2 points through the like legs, positive and negative, so UA and UB of the two thermocouples. We do that for 3 different currents, both positive and negative. So you can see the current direction changing, and this plot here shows us the results of a measurement. So you can see the voltage measured UA for 3 negative currents, and the voltage for 3 positive currents, and then the same for UB. So we have 2 sets of voltage measurements through the positive legs and the negative legs of the thermocouples. The distances, S1 is the distance between the current pin and the thermocouple on each side, and S2 is the distance between the 2 thermocouples in contact with the sample. So the equation to calculate the electrical conductivity appears here. So we are using the slope here of the change in current, the change in current over the change in voltage, and the distances S1 and S2. And finally, some correction functions, F1 and F2, which have to do with the geometry of the sample. And as we'll see, the SBA 458 is able to test samples of different geometry, disks, rectangular samples, different thicknesses. And these correction functions use finite element models to determine the equipotential surfaces that occur with different geometries. So these correction functions are related to this geometric factor for the shape and dimensions of the sample. So for all the possible dimensions of the sample, these correction functions were developed through the finite element, and they are applied when we calculate the electrical conductivity. Okay, so for the measurement next of the Seebeck coefficient, here's where we utilize our microheaters. So again, we can alternately heat one side of the sample and record the resulting thermal voltage as a function of temperature. So it's done in a cyclic process. So we heat one side, we wait for the maximum temperature gradient, we shut off the heater, it cools back down, and then we heat the other side. So during this entire process, we're recording the UA and UB. So this is the voltage drop from the 2 points where the thermocouples are in contact with the sample. We also record UT1 and UT2, which are the thermocouple voltages. So we have over 100 points here, which allows us to assure that we have a linear relationship. We'll see that this is part of our quality check. We'll have more on that coming up to really validate whether we've got the measurements set up correctly. So to calculate the Seebeck coefficient, we use the equation you can see here. So it's equal to the gradients of the curves UA and UB. So these are our curves here. This is the delta T versus the voltage. And so the slope of these two curves is A sub A and A sub B. And we multiply, we take the sum, we divide by the difference of those two gradients. We multiply by the ratio of the Seebeck coefficient of the two elements of the thermocouples, and we add the Seebeck coefficient for each of the elements of the thermocouple material A and B. And so this is the equation to calculate the Seebeck coefficient. So this process is done at each temperature step, again, by alternately cycling the heater on each side of the sample to produce a temperature gradient between the points where the thermocouples contact the sample. Okay, so we'll look now at the mechanical setup. This is again a picture of the SBA 458, and this is the mechanical setup. So when we open the furnace, this is what we'll see to mount our sample. So some of the features here, you can see the thermocouples and the current pins. So these are mounted on springs which are extended down into the cold region of the instrument. So they fix the position. This allows for a fixed position of the thermocouples and the current pins on the sample. So that distance remains constant during the test, and it's known, and we don't need to actually measure it for each measurement that we perform. So when the sample is mounted, you can see the support here. This is our ceramic plate. You can see the leads for the micro heaters here. And you can see these ceramic pins. So these ceramic pins are pushed down to compress the springs which mount the thermocouples and the current pins, and the sample is placed symmetrically on top of those 4 points. So the sample is across the support. So you saw this in the previous diagrams. So the sample is laid across the sample support, and then we apply a weight through mounting a pressure disc. So this pressure disc is actually a fused silica plate. Its position is controlled by these 4 bolts. So these screws will actually keep the pressure disc level so that it doesn't tilt onto the sample. And then this weight is placed on top of the disc to provide a constant force. So we want to have a constant force pressing down on the sample to maintain the contact between the sample and the 4 pins on the bottom. And again, those pins are mounted on springs so that we are compressing the spring to provide that constant force to achieve uniform and repeatable contact with the sample. Okay, so we'll talk a little bit now about the software which is available to control and analyze the data with the SBA 458. So when you click on the adjustment window in the software, you'll see the screen. So you enter some information on the sample name, identification, the shape of the sample, the thickness of the sample, the width, purge gas. So we can run measurements in different gases, oxidizing, inert, and also reducing. So you can determine the or record the purge flow rate. We also will enter a maximum current. So depending on the material and on its properties, we need to select a current maximum for the electrical conductivity measurement, and the software will calculate 3 other lower currents, which would be 1/3 and 2/3 of the maximum, and those become the 3 current values that are used in the electrical conductivity measurement. We also select the heater voltage. So the heater voltage has to be selected to give enough of a temperature gradient in the sample during the measurement of the Seebeck coefficient. So we want to get at least 4 degrees Kelvin across the sample during the Seebeck. And so this heater voltage has to be selected to achieve that. We can also select a number of repetitions. So this means when we program our temperature steps, we can choose to repeat that entire program as many times as we want. So here you see the temperature steps that can be programmed. You have a temperature and a heating rate to go from one step to the next. Typical heating rate is in the range of about 10 degrees per minute. And then finally here you see an emergency reset temperature and also the ability to shut off the purge at the end of the measurement or to delay that closing of the purge valve. Okay, so when we're ready to start our measurement, we go to we will see this window here. So the data that was entered previously in the adjustment window appears here. Our thickness, our width, our current, heater voltage, purge gas. You can also see here a temperature difference threshold and a stability threshold. So these have to do with controlling the temperature for the temperature steps where we heat the sample and we hold it. We want to hold it isothermally during the measurement process. And these graphs here show us the measurement. So we have our raw data here on the right of our voltage versus current. So these are our three negative current values, our three positive current values, and the resulting voltages that were measured. And then in the left window is the calculated electrical conductivity, Siemens over centimeters, for that point, which in this case was around room temperature. And then in the lower windows, we have the raw data for the Seebeck coefficient. So here we're plotting the delta T, again ranging up to, in this case, a little bit over 4 Kelvin, plus and minus. So again, we alternate heating one side of the sample and then switching it to heat in the opposite direction. And we record the resulting voltage during that process. So you can see the points here, and we produce a linear regression for each of these curves to determine the slope. And ultimately, the Seebeck coefficient is calculated, so you can see, in this case, a value of around minus 37 microvolts over Kelvin. Yeah, one other thing I want to mention is that as part of a quality check, which we'll talk about later, one nice feature of the software is that if once you're at the temperature, let's say you're starting at room temperature and you want to be sure that everything has been set up correctly, you can click the measurement button, and the entire measurement process to produce these plots will be completed, and then you can evaluate the plots before you start the temperature program. So this just saves some time in case there is something wrong with the setup. Perhaps the sample wasn't mounted correctly. You don't want to waste a lot of time doing the temperature steps over many hours. So you have the ability to do a kind of pre-measurement for a quality check of the setup. Okay, so now we're going to talk about some of the key features and advantages of the SBA 458. I've mentioned a few of them already. One of them is the flexibility of the sample dimensions. So you can see we can measure bulk materials, films, coatings. The case of films and coatings are normally going to be applied to a substrate. We can do rectangular and quadratic samples. We can measure round samples. So the round samples allow us to directly measure the same samples that are used for LFA. So if any of our participants are familiar with LFA, measurements of thermal diffusivity, in some cases specific heat, and ultimately thermal conductivity, we typically use a disc about 12.7 or a half-inch diameter. And that's actually the smallest sample size that we can measure with the SBA 458, and we can go up to larger diameters. But the flexibility in terms of the sample support and the measurement setup for different shapes, different lengths, and different thicknesses, and all of those parameters are included in the modeling corrections that are used to calculate the electrical conductivity. So we looked at fast and uncomplicated sample change. So because these current pins and thermocouples are fixed in the sample holder, there's no connections necessary. So there's no tools, and there's also no tools necessary. So the sample is placed on the support, as we looked at, and then the weights are applied on top of the sample, and the instrument is closed and prepared for testing. So, and also because of the fixed position of these pins, we don't need to determine the distances S1 and S2. Again, these are the distances between the pins, the current pin and the thermocouple, and between the thermocouples S1 and S2 when we determine the electrical conductivity. And the design of the fixture and the sample support allows for no movement of the thermocouples during the measurement. So this is important if, of course, you make a measurement of this distance and during heating the position of the thermocouples changes even slightly, that will influence our electrical conductivity calculation. So some other key features, we have a robust system. So robust in the sense of the thermocouples is that we use Inconel sheathed thermocouples. So instead of a bare wire, which could lead to contamination and aging of the measuring junction, we have Inconel sheathing. So the sheathing really prevents any interaction or sticking of the thermocouples to the sample and reduces any risk of contaminating the thermocouple through that contact. So, and especially if you weren't aware of it, you may, on a subsequent measurement, have an effect due to contamination of the thermocouple, so it's not measuring the temperature accurately. So this sheathing really makes for a robust measurement system. The sheathing, of course, also strengthens the thermocouples, so you're allowed to press them with some force onto the sample to give that positive and uniform ohmic contact between the pins and the sample, or the thermocouples and the sample, and that's very important for the measurement. So the fixing of the thermocouples gives us defined contact force, again determined by that mass and the compression of the cold springs, which we looked at. It doesn't give us any variation in the distance during the measurement. We don't need to measure that distance for the calculation. And as well, it gives us homogeneity of the contacts, electrical and thermal contacts. And one important feature is that these thermocouples and current pins can be replaced. So if they do get damaged for some reason, it is possible to replace them. So that is important. Finally, quality check. So we discussed this a little bit already. For the electrical conductivity, because we can measure the current in both directions here, this allows us to check the ohmic contact. So if there is some barrier layer between the thermocouple and the sample, so we get a shunt characteristic, it will show up in the nonlinearity. So we want to have linearity, and we also want to have agreement of the curves for UA and UB. Again, these are the voltages measured through the positive and negative legs of the thermocouples, both negative currents and positive currents for voltages applied in both, or current applied in both directions through the sample. So this is a really important check of the system. For the Seebeck coefficient, because we have a heater on both sides of the sample, we can perform the measurement in both directions as well. And so here we're looking for, again, a check of the contact for detection of any inhomogeneities, and that we have a symmetric sample position. So if there are problems with our measurement, it'll show up as nonlinearity in these curves and hysteresis. So again, this is as we are cycling the temperature gradient on the left and right of the sample, from left to right and then from right to left. As we vary the temperature, we record the voltage across the sample. So this is an important quality check for the Seebeck coefficient. And again, these can be performed prior to any measurement after the sample is mounted, which allows you to really validate that everything is okay before you launch your measurement. Okay, so to summarize, some of the key features: flexible sample dimensions, easy sample change, no measurement of the distance is required, robust system, Inconel sheave thermocouples, the positions are fixed, the pins are thermocouples and pins can be replaced. And then again, quality check for the measurement. We do a quality check of the electrical conductivity and the Seebeck coefficient through some of the unique features of the SBA 458, which allow us to validate the measurement. Okay, so some of the specifications of the SBA 458. It's a 2-heater system, integrated quality check, temperature range with the furnace and the sample support. We can do measurements from room temperature up to 800 C. This covers most thermoelectric materials, so it should be an adequate temperature range for determination of Seebeck coefficient. Temperature setting range, so we can set an unlimited number of temperature steps if you want a detailed curve of the electrical conductivity versus temperature and Seebeck coefficient versus temperature. The thermocouples are Inconel sheathed type K, again fixed position. Sample dimensions, I mentioned this earlier. The minimum diameter is 12, or length is 12.7 millimeters, and the maximum is 25.4. Width between 2 millimeters and 25.4 millimeters. And thickness should be 2 millimeters or less. And if you have a coating or a film on a substrate, this thickness is the total thickness. As far as films, we can measure films as thin as the micron range. However, one precondition is that the film must have ohmic transport and not ballistic transport. So you have to have electrical conductivity and a linear relationship between the voltage and the current to be able to do the measurement. But if those conditions are satisfied for the film, it's possible to do the electrical conductivity and Seebeck coefficient measurements. Again, sample geometries, square, rectangular, round. Accuracy, Seebeck coefficient and the electrical conductivity can be performed with accuracy of better than 10%. Repeatability is plus or minus 3% for Seebeck coefficient and plus or minus 7% for electrical conductivity. For atmosphere, we can run in reducing atmosphere with a maximum of 2% concentration of hydrogen, inert atmosphere, and oxidizing atmosphere. The system is also vacuum tight with a minimum pressure about 10 to the minus 2 millibar. Okay, so finally we're going to look at a couple of applications. This example is on isotan. This is an alloy similar to constantan, which is the one of the thermal elements for thermocouples such as type E. And we're showing measurements from room temperature up to 400 C for isotan. You can see the electrical conductivity in the range of 20,000 Siemens over centimeter. And the Seebeck coefficient here ranging from about 40 microvolts per degree, decreasing down to about 60 microvolts over Kelvin, and then comparing the Seebeck coefficient to reference values. So this isotan is a reference material for Seebeck coefficient, determined by PTB Standards Lab in Germany, and these are comparing the SBA measurements to the reference values, and the agreement is 10%, is under 10% in this case for these measurements. This example is a lead telluride, which is doped with bismuth. You can see electrical conductivity and Seebeck coefficient measured between room temperature and 250 C. This material is also a reference material for Seebeck coefficient. You can see the electrical conductivity in the range of about 300 to 500 Siemens over centimeter, and the Seebeck coefficient ranging from about -100 to about -175 microvolt over Kelvin. And then comparing our measured Seebeck coefficient to the reference values from PTB, again, the agreement here is better than 10%. Okay, so thank you for your attention. You can get more information on the SBA 458 on our website, www.netch.com, and follow the links to analysis and testing and products, and you can get more information. Again, thank you for attending, and have a great day.